Welcome to a lesson with Dr. Powell. Let's talk about how we can multiply two power series together. But first, let's talk about how we can multiply two polynomials together. Because remember that power series are just like infinite polynomials. So let's start with something like this. 3x cubed minus 2x squared plus 1. And let's multiply that by x squared plus x plus 2. All right, so let's line these line powers up here, are like powers of x. So constants, powers of 1, squared, and cubed. How do we do this? Now, we have a basic algorithm for multiplying two numbers together that are written in their base 10 expansions. The same thing applies here. We can use the same technique. Here we just have powers of x. The only difference is that when we're adding, we never carry because we can never regroup and send over into another column, especially since we don't know what x is in its variable. So we just stick to one column at a time as we add. But all the distributing is the exact same in the normal base 10 multiplication algorithm as it is here. So what we're going to do is we're going to strip these numbers of the variables and just look at the coefficients themselves. And also in differences, sometimes you have coefficients that are negative. And you could do that with base 10, but we don't usually do that. Okay, so then, and this would be a 1 in this position right here, and then a 1, and a 1, and a 1 right here. Okay, so when we multiply, we simply take 2 times all of this, just distribute the 2 to each thing individually. 6. All right, so we get this number. Now, the nice thing about one nice thing about this is, again, we're never carrying, so we just kind of multiply 2 and 2 and 2 and 2 and just put the results right here. Next time, this guy, remember this is ln x. So, and to all these powers of x, you're going to add an exponent of 1, which is going to have the effect of shifting everything over a place value. So when we multiply this 1, the result will be shifted over. So 1 times that whole line, simply the line itself shifted over. Similarly, this is like an x squared, so it shifted 2 times places over from the beginning. So 1 place over from the last place. So we're going to have a 1, 0, -2, 3. Now you just simply add 2, 1, -3, 4, 1, 3. And we end up getting 3x fifth plus x to the fourth plus 4x cubed minus 3x squared plus x plus 2. We just multiplied those two polynomials together fairly quickly using the regular base 10 algorithm because it exactly shows us how to distribute everything. Now we're going to learn from this to know how to series multiply together. So let's think about these different columns. This one where you got a 2, this was the only way that we could multiply something from this polynomial down here to this one to end up getting a constant. Let's write out what the polynomials were again. This is 3x cubed, 2x squared, plus 0x plus 1. This is 1x squared plus 1x plus 2. So notice something from here to something in here. Those are the only things you can multiply to get you a constant. Now, what about this? The only ways to get an x term would be to do a crossing like that, which is exactly what's here. This crossing is this 0, and this crossing is that 1. Now, what about to get this -3? So notice we have -4, 0, and 1. This -4 came from this right here, 2 times x squared. This 0 comes from this 1 times 0. And this 1 comes from that times that. Notice we have there, there, there. Those are the three ways of potentially getting an x squared. And we add those up. These are the ways of getting an x cubed over here. So let's see where that comes from. To find x cubed, we have either that way or that way. Or we have, let's see, this came from, or we have this way. Aha. So that way to get the 6, we have this way to get the -2, and that way to get the 0. There's 3 different ways here going across in order to get that 4. And so we can kind of go down the line and see what's happening. So in general, let's kind of get a sense for what's happening. Okay. Now, let's look at an example of 2 series being multiplied together. Suppose that we have this one. I'm going to use different indices other than n because we're going to have 2 different series that we're going to be multiplying together. So let's suppose we have this one, and it's just simply x to the j. All right, so just this one right here. This is a geometric series. And let's multiply this series to this one, k equals 0. This will also be a geometric to keep it simple. So we have, let's just do 2kxk. Okay, so I'm going to multiply those 2 together. Now the result is going to be a series, and we're going to be combining like terms, just like we were in the columns for the polynomial. That's an n, n goes from 0 to infinity. We're going to combine like terms and think about what the coefficient of x to the n will be. And so kind of like what will the columns be as we move along. Now we could, there's two ways we could do this. We could think through what's happening and figure out what goes here. We can also do it the same way that we were doing it, quite literally using the algorithm that we have for base 10 multiplication. Let's first think about it, and then we'll move and we maybe compare it to the other way. So think about what's happening. We're taking coefficients from this series times certain coefficients from this series in order to get a coefficient of n. All right, so it's kind of like we're taking something from an x to the j over here and something from an x to the k over here when we multiply those together in such a way that we're going to get an x to the n, meaning that j plus k itself will end up being n. So really it's going to be like the sum of, but just the coefficients, 1, and so 1 times 2k, where j plus k equals n. I mean, a j is kind of hidden in this 1. I mean, it's just a constant, but it came from x to the j here. So essentially, we're just looking for all pairs, j and k, that add together to make n. Well, the different pairs you could just run through. Let's say, because k goes from 0 through n, j will be going backwards. So as k goes from there, j will be running backwards, and n all the way down to 0. So really, we can just think about, since we only see a k here, we could just think about what's happening for k. Essentially, what we're going to be doing is just adding up all the powers of 2 from 2 to the 0 to 2 to the n right here. So it's going to be like 2 to the 0 is 1 plus 2 to the first plus 2 squared all the way up to 2 to the n. And that's going to be the coefficient of x to the n. Now, this is kind of an interesting a multiplication because we know what this is by our partial sums for for a geometric series, because we're adding up so many terms of a geometric series. That is, what we can do is we can see we have n plus 1 terms, so we can think, and we're multiplying by 2, so 2 to the n plus 1 number of terms minus 1 divided by 2 minus 1. And that's actually the coefficient of x to the n, and then we're done. We just multiplied the two series together, and we ended up getting this. 2 minus 1 is just 1 itself, so we really could just rewrite it out like this. And that's our series. Kind of nice. All right. Now, let's take a look at what this would be if we were just multiplying things out with using the regular base 10 algorithm. Okay, so we have one series is just ones, the other ones is powers of 2 for coefficients, starting with the x to the 0 term and both of them being 1, because 2 to the 0 is 1, then 2, and then 4, 8, 16, 32, and so forth. Here we just have lots of ones. So when we multiply these two, we think 1 times that whole line. So we get 1, 2, 4, 8, 16, 32. And the next time we just say 1 times that line, but we shift it over. So we're basically just shifting the line over every time. Then 1 times that whole line, we shift it over twice from the start, or once from the last place. So 1, 2, 4, 8, and then 1, 2, 4, and it then 1, 2, and it keeps going. Of course, we have a lot more to keep going on. Just kind of stopped writing it right at that point. When we add here, notice we have 1, here we have 3, here we have 7, here we have 15, and by inspection, I guess you could say, oh, let's do one more. So let's see, we have 10 and 15, so 31. By inspection, we notice that these look like, this quite literally looks like we're doing like 2 to the 1 minus 1, 2 squared minus 1, 2 cubed minus 1, and so forth. This is a 0, 1, 2. If we can kind of notice that these are just 1 less than powers of 2 as we move along, and it's just 1 more than the position that we're at. So here we're at position 0. Then we go 1 and then minus. Here we're at position 1, but we go 2 squared and we subtract. So we could just by inspection do this and note it and come up with a pattern for these guys and just write it down. I mean, that's okay too. Of course, the ideas, we can use the ideas and be kind of really sound in our argument how to get it, but nonetheless, we could see a pattern potentially. Not always easy to see a pattern, but in this particular case, there is a nice pattern. Now in the next video, I'll show you another method that we could have used in order to multiply those two series, and that deals with partial fraction decomposition. We'll get there in the next video. Thank you for watching.